where we left off with question 12. It's asking, we want something with a high melting point, so that's one bit of it, high melting point, which means that we are looking for something that is crystalline, but it does not conduct electricity, so we are looking for something that is covalent. We have an ionic compound when we have a metal and a nonmetal, which would have a high melting point, but it would conduct electricity when it's either dissolved in water or when it's molten. So we know that that is not the answer. Here we have iron. Iron is a metal. Metals absolutely conduct electricity, so we can rule that out. Sodium chloride is also an ionic compound, just like lead-2 bromide, so we can count that one out. And so we get to silicon dioxide. That one is crystalline. That's one of the things that people often forget. It's sand, and that's crystalline in shape. That's one that comes up a lot on IB exams. It's a giant crystalline shape for SiO2. But since it is a crystal and it is not ionic, it's not going to either become molten and suddenly become conductive, or it's not going to dissolve in water and become conductive, so it will not, under any state, be conductive. This one, we've got ethanol being burned in a water calorimeter, and we're trying to figure out, based on water, what our Q is. So we've got nice of them to give us. Q is equal to MC delta T. Luckily, we didn't have to remember that equation on our own, so that's what we're looking for. But, and that's one of the reasons I put the line under here and I made it a little too long, when we're looking at it, all of this information would be for the water. The mass of the water used, the specific heat capacity of water, which is given to us, the change in temperature of the water, because that's the one that we're measuring. But we want it related to the ethanol, so we have to determine how this is related, and here we see what we're looking for. It's going to be something in kilojoules per mole, so we need to have at the bottom here the mole of the thing that is burnt. In this case, it's ethanol. So let's move this to where I wanted it. Right down here. So it's on my denominator. After I get through everything, that's what I'm going to want on the bottom. There's a few things here. We're given the molar mass of the ethanol, and we are also given the grams of ethanol that is burned. So I'm going to have to do a little bit of stoichiometry. And again, this is hard to do with this program, but, or at least quickly with this program, I take my given, that's 0.46 grams of the ethanol, and I'm just going to convert it using the molar mass to moles. So I would put 1 mole on the top, the thing that I want, the unit that I want goes on top, and the 46 grams of that thing goes on the bottom. So I've got that part. That would be what I would put on the bottom, my denominator, of this equation. And let's see if there's anything else that we need to change. We've got the mass of the water in grams, that's perfect. We've got the specific heat capacity of water with units that we like to use, and we've got that the water is raised by 3 degrees or 3 kelvins, which is a change in temperature. It's saying that it's already done that math for you, that delta T, the final minus the initial, it's given that to you already, so you don't have to calculate it. It's already in the 3. We look here that we've got the 0.46 and the 46 in each of these. So we just have to figure out what happens when I've got this. Remember from our previous video that when we have 1 over a fraction, that fraction gets inverted to get to just one number on the denominator. So that means that this 46 is going to be moving to the numerator when I type it all in. So my mass of the water, 500, has to be on the numerator, and I've got that in 3 of these in the numerator. It's not in this one though, so I can cancel out that one right away. And then my C, my specific heat capacity of water, is also on the numerator, so I'm looking for ones that have 4.8. Those all do, so I can't cancel any of them out. Same with my delta T, my change in temperature, 3 Kelvin. That is on the numerator and on the numerator, but this one's trying to do something funny. It's saying it's trying to trick you because the 273 plus something in Celsius would be in kelvins, but it's already given it to you in Kelvin. So as long as you were paying attention, you would know that B is not the correct answer, so we can cancel that one out right away. And then we get down to the last two. Both of them have the 46 on the numerator, which is good. It knew that this might trick up some people, that it would become on the numerator when it's dividing by a fraction, but it just put it on both of those right away. So then we have to look at what's left of it. This one has 0.46 on the bottom. This one has 0.46, but it also has a multiplied by 1,000. So we have to think about what it was talking about with why would it be in 1,000. And actually, if we read the problem again, we're looking at wanting kilojoules per mole, but my specific heat capacity is in joules. Haha, so it's making sure that you recognize that the kilojoules and the joules are not going to be equivalent, and that you are going to have to do a little bit of converting to get from joules to kilojoules. And that's where this 1,000 comes in, because my answer would be in joules per mole when I typed all of this first stuff in, but I want it in kilojoules. So I remember that there's 1,000 joules in every kilojoule, so I would have to divide by 1,000. C is my correct answer. So much to look for there that we had to remember. Lots of little places that we could have messed up. So write lots of stuff. That's one of the nice things about these examinations. You can write all over the multiple choice section if you want. The multiple choice sections come back to me more than 24 hours after the exam is completed. And so I get to keep those. IB doesn't get this, so they're not going to see all of the work that you do. So don't anticipate that they're going to, that you're going to get graded on that, because you're not. But you can take all of that space and write whatever you want to make sure that you've got your right answers. Moving on to question 14, we're looking for the average bond enthalpy of the carbon-hydrogen bond. One of the things about average bond enthalpy that you should remember is that it's got to be in gases, so something where everything are gases. And we can see right off the bat that D has some solid in it, so we cannot use that one. We are looking specifically for 1 mole of that atom, that carbon-hydrogen bond being formed. And so we would end up with C as our answer, because we're looking for one that has a mole of each of the atoms. There's 1 mole of the hydrogen atom there, there's 1/4 of 1 mole of carbon there, and so we would end up looking just at the carbon-hydrogen bonds that we've got there. Okay, question 15. This is using Hess's law, and it's not giving you actual numbers that you have to use to calculate. They're trying to make it a little bit easier on you. But you're going to have to remember that the standard enthalpy of formation, we're looking at forming methane. So I need to know which thing here is methane. Well, the methane that we have is right here. Unfortunately, that's not being formed. It's a reactant. So we're going to have to flip this equation. So we'll do a line, and we're going to flip it. So that means that I am going to have a delta H that is a negative G. Let's see if it'll let me make a G. Yeah, negative G. So my delta H for this reaction would be a negative G. I'd also have to make sure that I can cancel a whole bunch of stuff out. I want to get to a final equation where my carbon plus 2 hydrogens, 2 diatomic molecules of hydrogen, so 2 H2s, 2 H2s is going to yield my methane, CH4. There we go. So that's the target equation that I'm looking for. I've got the one carbon there, that's good. I've got some oxygens though and carbon dioxides that I'm going to have to figure out a way to get rid of. Luckily I've got them in other equations as well. And here I've got just one hydrogen, so that means I'm going to have to multiply this equation by 2. So I'm going to have 2 F's. There we go. And I said I didn't need to do anything to my E equation. So I've got an E as well. So E plus 2F minus G. Look at this sample one that they've done. They've got 2 of the correct answer. That's a shame. I'm sure that something like that would not come up in your actual examinations because that would be horrible. And they've gone through many drafts and many people trying them before they send them off to you. So I am positive that you won't have to deal with anything like that, though in the sample test, C and D would both be the correct answer. Let's move on to 16. With the Maxwell-Boltzmann distribution, we've got 2 different temperatures, and we're saying that the temperature 2 is greater than the temperature 1. So we need to try to remember what that does to the Maxwell-Boltzmann energy distribution. One thing I want to remind you about these is that the number of particles is under the graph. So normally we think of things of being on the graph or on the line, on the best fit line. We think of those sorts of things, but really the number of particles is what's under the chart. And at a specific point, we end up with an actual reaction. So let's say this is my activation energy here, the amount of energy that's required for the reaction to take place. Under T1, this first line, I've got that number of particles that would react, but when I've got T2 here, I've got more particles that could potentially react, assuming that they hit with the correct orientation when they actually collide. Remember that particles must collide for a reaction to actually take place. So in this one, it's saying that my Boltzmann energy curve is shifting to the right, which is not what happens when my temperature changes. What happens when my temperature changes is that my peak changes and it moves, it's like it's smushed. So it's getting smushed down. My T2 looks smushed compared to my T1. I would end up with more particles after that activation energy that could react because more of them would be at the correct kinetic energy because it's got the faster temperature. So C is the correct answer. Flipping the page. We are looking at rates of reaction, and so we have to think of what different things end up affecting rate, and it depends on the types of reactants that I have. In this instance, I have a solid reacting with an aqueous solution that's acidic, so I have to think of the different things that it's telling me here. The first one is saying that I'm using larger clumps of calcium carbonate. That would actually decrease the rate of reaction because we are decreasing the surface area if I've got just larger chunks of it, so it would decrease the rate. So I know 1 is not my answer. Here we say we're increasing the temperature of the reaction. That should be speeding up the particles, and therefore if they're speeding up, they're probably going to hit more often with that amount of energy, the activation energy or higher, that's required for the reaction to occur. So this could very well be something that would speed up my reaction. And then we've got increasing the concentration of hydrochloric acid. That's kind of like my surface area. It's increasing the amount of particles that are available to react. And since it's creating more that can react, that should be a good answer as well. So both 2 and 3 should be correct, which means C is my correct answer. Then we get to question 18. We want, we've got an equilibrium equation here. I'm forming H2CO, but I'm also going in the reverse reaction and forming more of the CO and H2 at equilibrium. and I've got an exothermic reaction because I've got a negative delta H value. I've got gases. I've got 2 moles of the gas on this side. I have 1 mole of CO2 and 1 mole of H2, so 2 moles of gas. On the product side, I have 1 mole of H2CO. Okay, now I can start looking at my chart and figuring out what combination would give me the maximum yield of the H2Cl, methanal. Remember, al stands for an aldehyde. Meth because I've got just 1 carbon. After that aside, let's see, we've got an increase in pressure. If I increase the pressure, so I have a higher pressure, I'm going to shift to the side as a reaction to the stress that I've caused by increasing the pressure that has more or has less particles on it. So that would be shifting to my product side, the H2CO, the methanal. So that's one that I want. I like that high pressure. So it's either going to be A or B. We know it's not going to be C or D. Next we'll look at the temperature. We can either go high or low, and it's based off of the fact that this is an exothermic reaction. One way I can think of this is as my teeter-totter that I did with concentration, but I can treat, since it's exothermic, heat as one of the products. I should write that out instead. Oops. So, heat. So if I treat that as one of the products and I have lowered the temperature, that would mean I would set a stress on my system. Let's see if I can draw a triangle here. There's my teeter-totter. I have reduced the heat. I have lowered the heat. That's the stress that I have put on the system. To counteract that stress, the system has to shift to the right to form more of that heat, and in so doing it forms more of the methanal, which is what we're looking to see. We want to see more of the methanal form, so A is our correct answer. If I went in the opposite direction, if I increased the heat, my teeter-totter would go in the opposite direction. It would go towards the other side. It would form more of the CO and the H2. Okay, number 19. We are looking for which one is not amphiprotic. Amphiprotic means that I have to have a proton, so I have to have a hydrogen. And the ampha part of it, and the reason I was specific about the fact that it has to be hydrogen, sorry, I've got a cat that is attacking me right now. There's 2 words that are very similar, amphiprotic and amphoteric. Amphoteric means that it can act as both an acid and a base, and amphiprotic also means that it can act as both an acid and a base. The difference is that an amphiprotic has to include a hydrogen. There has to be a way for a hydrogen to come in and a way for a hydrogen to leave. So it's acting as an acid and a base using a hydrogen. That's Bronsted-Lowry's definition of acids and bases that we're using there. If we want to get more broad, the amphoteric could be using Lewis's definition of acids and bases, where electrons are exchanged, that broader definition of it. Hydrogens don't have to be involved. But this one's asking for amphiprotic. We need a spot where a hydrogen could come in and a hydrogen that's on it that could leave. The only one, and I don't know why it's bolded here, you won't be that lucky on the exam and have the answer bolded. This one's bolded though. I think that's funny. This is an acid right now, or it's the product of an acid in water. But all that it can do, it can't take in another hydrogen. It has to donate a hydrogen to. That's the maximum thing that it could do. So that one is not amphiprotic. Each of these could take in 1 more hydrogen, and they each have 1 hydrogen that they could share. Number 20, which species will react with dilute hydrochloric acid, HCl, to give off a gas? So I'm looking for either, if I'm dealing with acids, I'm looking either for CO2 or H2O, so carbon dioxide, or sorry, it's carbon dioxide or hydrogen, H2, not water. Looking at these, we've got 3 that are similar. the first two, A, B, and D, are all, let's see if I can do, boom, boom, all three of those are dealing with an acid. Let's move this. Acid plus a base that's either an oxide or a hydroxide. That's what each of those are. And when I have an acid with a base that's either an oxide or a hydroxide, I'm going to form two products always, and one of them is water, and the other one is a salt. It's an ionic compound from the reaction of an acid and a base, a salt, or an ionic compound. So that's what all three of those are. So I don't see any H2 gas or any carbon dioxide gas here. So that leads me to think that it's going to be C. But let's look at why that is. And we'll talk about the third type of acid reaction before we finish this one up. I've got a carbonate, and anytime I have an acid plus either a carbonate or a hydrogen carbonate, which are both bases, all of those molecules would be bases still. This time, though, they're not oxide or hydroxide bases, they're carbonate or hydrogen carbonate bases. They're going to form those same two products that we had before, water and a salt, but they also form carbon dioxide gas. So this one would be my correct answer. I want to remind you, though, too, before we stop here, what our third type of reaction is with acids, and it would be acid plus a metal. Acid plus a metal ends up yielding hydrogen gas as well as an aqueous salt. And all of these salts up here are aqueous. I could have put that in just as well, but the addition of water here insinuates that it is aqueous. We don't bother writing the water here because that makes balancing very messy. So that would be our place where we're going to stop.